Hello, in this video we're going to find the value of this integral here going from 0 to infinity of 1 plus x squared raised to the nth power. This is one or two steps into something that I want to show. It's pretty neat, and if you can guess it in the comments, that's pretty impressive. And so we'll leave the surprise couple videos after this. But to evaluate this, let's look at n equals 1 first. And so it's 1 plus x squared raised to the first power. Well, this integral here is the arctangent of x, and then of course we evaluated its limits, and as it goes to infinity it's pi over 2, and if you plug in 0, it's 0. So the answer is pi over 2. And I solved this in great detail in a video that I put out, sample actuary exams, prob and stat exam 2 of 8, part 2 of 6, if you want to know the details of that. Now let's look at the general n here. So this is what we're trying to solve. And let's set up a du or a u-dv substitution or integration by parts. So if we let u equal this part here and dv equal this part, so the derivative of this is this part. You know, the minus n comes out front and the 2x is here, and then you raise it to the n plus 1. dv is dx, so v is x. Then we take this piece and then this piece. So the first one is this, and this is what we get. And then it's minus this times this, but the minus makes that a plus. The 2n comes out front. X times x is x squared, and we get this 1 plus x squared raised to the n plus 1. Now here, when you stick in infinity, this dominates this. So this goes to infinity so much faster than this that it goes to 0. And you can use L'Hopital's rule to show that. And then when we plug in n, we get 0. So actually this piece here goes away, it's 0. And we're just left with this piece. So this equals this. Now the next step, we're going to use a trick where we say plus 1 minus 1. So we add a well-chosen 0, but then we're going to look at it in two integrals. So the 1 plus x squared, and then we're going to have the minus 1 separately. And so that's what we do here. So the 1 plus x squared, and then that's the minus 1. And then the 1 and minus 1 cancel, and we just get x squared. So these two is equal to this. And then this cancels with one of those, and then we just get whatever that is. So we're at this stage here. Now we're going to rewrite this to make it much more obvious. Now notice that we started with this, and this piece looks just like it, and then this piece here looks like this, but it's to the n plus 1. So if we call it v of n, so whatever the value is with the general n, that's what this is going to be. It's 2n times vn minus 2n times v of n plus 1. Right? So we have this relationship here, and where vn, of course, is the value of this when we use n. Now let's rearrange this and solve for vn plus 1, and we get this. So we take the other side, subtract that, we get this. But let's, instead of writing the n plus 1 to n, let's make it go from n to n minus 1, and that's what we do. So we have to stick in n minus 1 wherever there's an n, and then we come up with this. Now let's evaluate this. So what we just showed is that Vn is equal to this quantity here. But we could also do that with Vn minus 1, Vn minus 1 I mean. And then it's this quantity. And we could keep doing this until we get to V2, which is, you know, you keep subtracting the right numbers and it's then V1. But we calculated V1, that's when we used n equal 1, and we said that was pi over 2. So if we back substitute all these, then we get this quantity here. So this first fraction, the second fraction, times, and then this here is 1 divided by 2, and then V1 is pi over 2. Now notice here, it's 2n minus 3, and then we subtract 2, and then we subtract 4, and then that's called a double factorial. So we have n minus 3 double factorials. It means skip 2 instead of, you know, a factorial you go down by 1 and it's the product. A double factorial means you skip 2. And then it ends when you get to a 1 or a 2. And so that's this bottom one is also double factorial. And we get this. Here, you know, we end with the 2 and it's those. Here we end with the 1. Now, a couple notes here that we're not going to prove, but if n is odd and we take gamma of n over 2, then you can show that you get this relationship. It's basically n minus 2 minus 1 times gamma of n minus 1 over 2, and then you keep repeating that until you get down to gamma of 1/2, which is pi over the square root of pi. But you've done it this many times, you know, n minus 1 over 2 times, and then that you're going decreasing by 2. So anyway, this is a relationship that holds. And also there's another relationship for double factorial. If n is even, double factorial is equal to this. And there's, I think, some nice videos on how to show that. So we're going to use these two pieces. So this bottom part, this is an even number, right? So we can replace it with this quantity, something like this. And so let's do that. And so pi over 2, we're going to write square root of pi, and then we have 2. And this part here, using this formula, is this. And now this just stays the same. But now if we use this formula, we get this relationship. So this is a gamma, right? So this is gamma of n minus 1/2. Or you could say 2n minus 1 over 2, but I'll write it like this. And n minus 1 factorial is gamma of n. And then we have square root of pi, that's gamma of 1/2. And then we have this extra 1/2. Well, this piece here is it's called a beta function. So if we take our 1/2 out front, and then we have beta of 1/2 n minus 1/2, and that's the answer. I just think it's so neat and so slick that it reduces to that. Well, anyway, that's all I have for today. Hope you enjoyed it. I sure did. Please like the video so you don't miss the next one. And also, if you can guess what my ultimate goal is using this formula, I'll be pretty impressed. Anyway, see you next time. Bye.